in radioactive disintegration series, except the 4n plus 1 or the Neptunium series. There is a gaseous emanation. That means there is an element of a zero group that comes or that is formed in the form of, in the gaseous state. Nothing but radon. Okay. Except in Neptunium series, we get this in all other series. Now, this gaseous element is given different names. See, in 4n or thorium series, it is called thoron. In 4n plus 2 or uranium series, it is called radon with the original name. Whereas in 4n plus 3 or the actinium series, it is called actinon. Okay. These are the different radioactive series, which of course can be remembered this way. This is 4n AUNT on 4n plus 1, 4n plus 2, 4n plus 3. Okay. Let us now go for the kinetics of radioactive disintegration. Let us first go for the rate of decay or disintegration, or is also known as activity. Now we know that all radioactive disintegrations are of first order type. Yes. Let us consider a radioactive decay. A giving rise to products. In this case, rate of reaction with respect to A, the reactant or the parent element can be given as minus dN by dt, where N refers to the number of atoms. It is directly proportional to the number of atoms left at that time. Left at that time. Okay. So rate of decay or activity can simply be given as directly proportional to N. Now, this can be written as equal to lambda N, where lambda is a constant called decay or a disintegration constant. Okay. Activity can simply be given as lambda N, or rate of decay can be given as equal to lambda N. Okay. So let us take it as minus dN by N is equal to lambda into dt, or dN by N can be written as minus lambda dt. Okay. Now taking the integration. On integration, we get ln n. This is equal to minus lambda t plus constant. Okay. This is log base E, right? Now, see at a time t is equal to 0. That means when we are about to start the process, the number of atoms left will be the number of atoms that we have started with. R is nothing but initial number of atoms. Okay. Now, similarly, on the other end, at a time t is equal to 0, we can write the constant as equal to ln n, right? Considering two things at a time. So from these two, we can write that the constant is ln n0. Now substituting this in this expression, what do we get? Ln n is equal to minus lambda t plus ln n naught. Okay. Now from this we can actually write a useful form, just like the Wilhelmy equation, what we have written in the first order reaction. N is equal to N naught into e power minus lambda t. Of course, taking logarithm of this will give you this. Okay. And this also is a very important relation. Next. So the same can be written as ln n naught minus ln n is equal to lambda t. Okay. Therefore, lambda is equal to 1 by t into ln n naught by n, or converting this into base 10 to 0.303 by t log n naught by n. Okay. Just like the first order rate constant expression. See here, n naught is the initial number of atoms, n is the number of atoms left at a time t. Okay. Now let us take half-life. Half-life is the time required for the initial number of atoms to become half. Right? Let us consider T as a T half. Then in that case, number of atoms left will be half of the initial number of atoms. Okay. Now substituting this in this expression, we get lambda is equal to 2.303 by t half into log n naught by n naught by 2. Log 2 is 0.3010. Therefore, the final expression can be written as t half is equal to 0.693 by lambda. Isn't it? This log 2 is 0.3010. 2.303 into 0.3010 is 0.693. So this is the expression for T half. From this, it is very clear that a T half in this case is independent of initial amount taken. Okay. Coming to average life, represented by this or this, a kind of tau. As such, average life is nothing but the sum of lifetimes of all the nuclei by the total number of nuclei. Simple average thing. Sum of the lifetimes by the total number of nuclei. But you know, it is very difficult to know the lifetime of a radioactive element. That is the reason why we have gone for half-life. Because radioactive substances go on disintegrating, go on. So it's very difficult to say the overall lifetime of a radioactive substance. So when you cannot say the overall lifetime of a radioactive substance, it is difficult to calculate the average life taking this relation into consideration. So we can go for this. Simply the reciprocal of disintegration constant. Okay. Now, we know that lambda is 0.693 by T half, right? So this can be finally written as 1.443 or else simply 1.44 into T half. Okay. So this is a very important relation. Then this also. The relation between average life and the decay or disintegration constant. Then this is the relation between average life and the half-life. Let us see branch or parallel path decay. Now we know what a parallel path decay is. Let us suppose a radioactive substance A is disintegrating into B as well as a C in parallel path. Into B by the emission of alpha particle with a disintegration constant lambda alpha, and into C by the emission of a beta particle with a disintegration constant of lambda beta. We know that lambda average is nothing but lambda alpha plus lambda beta, right? Similarly, the fractional yield of B can be given as lambda alpha by lambda average, nothing but lambda alpha by lambda alpha plus lambda beta. Similarly, the fractional yield of C can be given as lambda beta by lambda average. Nothing but lambda beta by lambda alpha plus lambda beta. Okay. It's by total. Let us see what is radioactive equilibrium. Unlike the normal chemical equilibrium, what we see, radioactive equilibria are irreversible, cannot be taken back. But still, how to explain what a radioactive equilibrium is? Let us consider a radioactive decay. Say A giving rise to B, B giving rise to C. In this case, the disintegration constant is lambda A, and in this case, it is lambda B. So this is how it goes on. And see, at equilibrium, considering this B, we can state what radioactive equilibrium is. You know, at equilibrium, the rate of formation of B from A is equal to the rate of its disintegration. I mean, rate of disintegration of B into C. So this is how we can give. Formation of B from A and disintegration of B into C will have the same rate at equilibrium. Say this rate of formation of B can also be given as rate of disintegration of A, right? Because A disintegrates to form B. Now let us keep it as it is, rate of disintegration of B. Okay. Now rate of disintegration of A can be mathematically given as minus dN by dt, of course, dNA by D, because it is the number of atoms of A left at that particular time on which the rate of disintegration of A depends. In this case, it can be given as minus dN B by dt. And we know that minus dN by dt is equal to lambda into n. So in this case, let us write this as lambda A into NA is equal to lambda B into NB. Okay. Or the same can be represented as lambda A by lambda B is equal to NB by NA. And say lambda and T half are of course inversely proportional. So T half of B by T half of A. Similarly, lambda and average life are also inversely proportional. So it can be given this way. So this is very important. You got all the relations in this. Now coming to maximum yield of data element. As I said, if we consider this, in this we call A as the parent element, and B, of course, because it is disintegrating into C, it is the product, but we call it daughter because it is further disintegrating into C. Then even C also disintegrates, and this process of course goes on. Okay. Now considering this particular disintegration series, say at a time t is equal to 0, where the number of daughter elements is a 0, and if the parent has a longer lifetime or half-life, you can say, is much more lived than the daughter. How can we say that? Like you can use lambda A is less than lambda B. Because lambda and T half are inversely related, right? So if lambda is less for A, its half-life is more, that means it is much more lived. Look at more half-life than B. Yes. In such a situation, you can also use the terms Ka and Kb also. In such a situation, the number of atoms of daughter element at a time t can be given as NB is equal to N naught into lambda A by lambda B minus lambda A into e power minus lambda a at a time t minus e power minus lambda b at a time t. Look at this carefully. Number of atoms of daughter element at a time t, that is nb, can be given as n naught into lambda a by lambda b minus lambda a into e power minus lambda a into t, isn't it? It is like e power minus lambda into t. So this has to be minus lambda b based on the same relation what I gave. That is n is equal to n naught into e power minus lambda t. Just a modification of that. Okay. So this can be given as minus lambda a into t minus e power minus lambda b into, okay. One more very important thing, that is the time after which daughter element will have maximum activity can be given as Tmax, nothing but 2.303 by lambda b minus lambda a into log lambda b by lambda a. This is a very important relation. Tmax, time after which the daughter element shows its maximum activity. Okay.